Guten Morgen. I'm going to make another video. Here we go. Let's get started. I'm going to share my screen. You don't have to look at me anymore if you don't want. I'll even make this small and put it in the corner. All right. So, we're in Algebra 1. We've gone through all of constructing graphs. We're now at multiple representations in the real world. We're going to do tiling square pools. I'm going to try to do this and be more explicit. So this is my second try at this video. All right. So if you remember in a previous section, in a previous section, we were talking about tiling around a pool. This pool, some of you got this wrong. Now we talked about this very explicitly in class, but I understand if you missed it. Make sure that you try really hard to get the answers and stuff like that. But there was a pool, it was 3 meters or 3 feet on each side, which is 1 yard on each side. So I could put 3 on each side of it for a total of 16 when you add the corners in. And that was a concrete representation, and we filled that in. That was called Tiling Square Pools Overview. And now we're going to continue with that situation because that was the Chen family. They were doing that, and so they're going to get, Mr. Chen wants to make sure that everything goes well. He doesn't want to waste money on mistakes. So he has asked Anthony to use his math skills to plan ahead for some of the projects. And Anthony's planning will save time and avoid costly errors, which is part of why we do math in the first place, is to model stuff so that we avoid errors. That's why you never start a building without a blueprint nowadays. The company does a lot of tiling work that is exactly like his first job. So here's his first task is to notice that there are relationships between how long the sides of the pond are and how many tiles that go around the outside of it. The longer the sides of the pond, the more tiles it takes to go around it, obviously, because of the bigger pond. We're going to explore that relationship in different ways. So he considers the problem. He knows his dad wants him to work with square pools. So although he doesn't know exactly how big the pools will be, he knows that they will be square. He decides he's going to use 1-foot square tiles for the borders. Well, since they use those, he assumes that all the pools will also be measured in feet, whole feet, 1, 2, 3, 3 feet along each side, for example. Not 2.5 feet, not 3.25 feet, no, 3 feet. And so he's decided he's going to limit what we call our domain, because he's saying the size of the pool, that's our independent variable, affects how many tiles go around it. So this is our independent variable. What it's allowed to be is called the domain. So I'm allowing a domain of 1, 2, 3, but not 2.5 squares. Okay, so that's what we're talking about when we say our domain is limited. All right, in real life, we call those parameters. Since the company uses that, yes, so he will use only full square tiles for the thing. He's not going to use fractions of tiles. He decides to look at the pools that have sides measured in whole numbers of feet, like we said. He starts by making a concrete representation of the situation. He uses small plastic tiles to make a 1 square yard pool. That's it right there, 1 square yard. We're going to make the smaller pools. So here's Anthony's 1 square yard pool, and we figured out that requires 16 tiles to go around it. What would his 2 smallest pools look like? By the way, these are the first questions in the assignment. I'm going to try to be more explicit. So think about this. What are the smaller pools? I'm stopping for a moment. Please figure it out and then push play. Pause. I'm assuming you thought about this and are now moving on. Well, this is a 3 by 3 pool. I can also make a 2 by 2 pool. Oops, that's not right. I'll move in a sec. Ooh, oops. There, 2 by 2. That's smaller. 3 by 3, 2 by 2, and the smallest I could get is 1 by 1. So those are my 3 pools, and I can check it. And it says, great job, you're correct. Now fill the table to show in the length of each pool based on the sides you built. So this one is only 1 square foot, or 1 foot on each side. In this case, it's 1 square foot. This one is 2 feet on each side, 4 square feet. And this one right here is 3 feet on each side. That's 9 of these little squares, 9 square feet. Great job. Now we're going to figure out, you'll build borders around each pool. Now going to the assignments, just so you understand. Modules, here's our assignment. It is called, oh no, it's down here, Tiling Pools Worksheet. There's a video. I'm kind of replacing that right now because I was not explicit. And I want to make sure I'm explicit. So I can open it, and remember, we're going to open things in Kami. So if you open it up like this, usually there's a Kami up in the top corner, or you can open up Kami after you download it. And there's lots of ways to do it, but see, I've got this guy. Maybe I do need to download it first. That's fine. I will open this, download it, Square Pools 5. I'm going to open up Kami. I'm going to go find Square Pools 5. Open from computer. Square Pools 5, that'll do it. And new copy. All right, so now I've got it open in Kami. So we noticed that the two smaller pools were, I'm going to use squares, a 1x1 square pool, and what just happened there? File is not uploaded. Dismiss this, always upload. Save to drive, that'll work. Okay. Let me get rid of this. And the other one that we had was a 2x2 square pool. There's one square. I wonder if I can copy you. Control C, Control V. Now I can move y'all. Ugh, these things are too big. It won't let me move them. That's really annoying. Okay, well, we're not trying to work that hard. And we have our 4 square foot pool. So those are the two smaller ones. Make a sketch. Great. We just did this. We said if the pool is 1 on each side, well, we're about to do the tile border, so let's take a look at it. Okay, so we got our pools 1x1, 2x2, and 3x3. What if I need to put tiles around them? I am going to painstakingly put tiles around this. 4, 5, 6, 7, 8. Takes 8 tiles to go around the outside of that one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. It takes 12 tiles to go around the outside of that one. 1, 2. We've done this one before, but I might as well be thorough. So we're trying to figure out how many tiles it takes to go around each of these pools. And the pools are getting bigger. And the bigger the pool, the more tiles that go around it. Oh yeah, we're like close to 10 now. Seems like even though I pull tiles out, they never run out. Kind of crazy. Okay, there are 16 tiles around this one. So if there's 1 foot on each side of the pool, it takes 8-foot long tiles to go around the whole thing, including the corners. 2 takes 12. 3 feet on each side, takes 16 tiles to go around the outside. Not exactly what you would guess off the top of your head. And that's kind of the fun of it. So I'm putting this table into my assignment because that's what we're doing here. So I go over here and I say 1 requires 8 tiles. 2 required 12 tiles. 3 required 16 tiles. Hopefully that makes sense and it's really simple. What does the pattern reveal? How much does it connect to the model? Okay, we're going to go back to that and we're going to try to ask ourselves, what does this do? What do we notice about the tiles in these numbers? As we go on, we're going to talk about that. What pattern does this numerical representation reveal? Well, you may notice that this is going up by 1s and that's going up by 4s. That's a good one. What's this say? Oh my gosh, every 1 foot I add, it seems to add 4 tiles to the border. Now, that might seem like the solution or something, like, oh gosh, I just solved the problem. It seems that when adding 1 foot thought to the side of the pool adds 4 tiles to the border. That's our guess. Now in math, noticing this in a table is technically not enough. We need to really, really, really prove things in math. But it's good to notice this and go, that seems to be the pattern. Well, a function rule would show that general relationship. And that's what we're going to shoot for, is a function rule, which show that general relationship. Now, when we say function rule, we mean an equation with x and y, or p and s to stand for the pools, borders, and the side. I don't know. You're going to figure out that as we go, but it's a formula. That's what we mean when we say function rule. All right. Anthony wants to find a function that will let him find the number of tiles needed for the border of any size square pool. Study the animation to look for connection between how the concrete models and the numerical model will help Anthony find the rule. What is the same for every pool and what changes? That's the question. All right, so we're gonna push play. Here's pool number 1. It's 1 by 1. It's a tiny little pool. Now notice what he's gonna do is he's going to go like this. Yeah, I do. He's going to notice that there are 4 sides to the square pool right here, and each side is 1 foot long for a total of 4 times 1 tiles, which is just 4. All right, and then he also notices we have these corner tiles. They also have to go in there. Now notice, when we make the pool bigger, some things will change and some things will not. When I make the pool 2 by 2, there are still 4 sides, but each of those sides is 2 feet long. And there's still 4 corners. And the corners are still exactly the same. They have not changed. That's why they don't get multiplied over here. They're just little add-on at the end. So now I have 4 sides and each of them is 2 feet, for a total of 8 tiles around the sides, plus the 4 corners, for a total of 12. Then when I go on, I get 4 times 3 plus 4. So now I have 4 sides and they're each 3 tiles long, plus the 4 corners makes 16. So if we can construct it and show what's going on each time, then we're in good shape because we can see where the pattern is coming from. We can trust that it's going to continue. But we have not written the symbolic rule, the function rule yet, and that's our next question. So we've thought about this, and here's the thing we notice. Whatever the side is, I multiply that by 4 because there are 4 sides. And so the length of all 4 of those sides should be the length of one side times 4. I get all 4 of them. And then the 4 corners. So if we think about that, I want you to think, what would I replace if I made one of those X and one of those Y? What would this look like? I'll give you a hint. 3 is one variable and 16 is the other one. So what are these? If I change them to variables, what would that look like? And then we'll have our formula rule, okay? So notice, study the process column in the table. They call this a process column. We can try and do that. It's not important to call it a process column. This is just a way to think about what's going on. But that's what they're calling it in this book. So you might as well know that. What stays the same, what's different? Notice the 4s are all the same. 1, 2, and 3 change along with this one. They are the variable. So the pool length goes here, here, and here. So if I make a formula, I'm going to have the 4s. This is times, and this is plus. So I got my 4 and my times, and this is supposed to be the pool length. What stands for the pool length? S represents the length of the pool. Okay. So now I have 4 times whatever the pool length is, plus 4. This is my formula. And that makes the number of tiles in the border. So if I multiply this times 4 and add 4, I should get this number, which is the number of tiles in the border. So the number of tiles in the border should equal this. And now I've got my formula, T equals 4S plus 4. I can type that in here. T equals 4S plus 4. Boom. Or you can say T equals, oops, do a very good job with the spacing. I like to space between those. Equals 4 shift 8. 4 times S plus 4. You could do that too, if you like to write the multiplication in. But remember, when we start having letters and numbers together like this, we have multiplication between a variable and an actual number, numeral, then you don't have to write the multiplication between them. That's just like a grammar thing. It's not like something fancy. It's just, oh, people got lazy and they stopped writing this multiplication. They were like, well, let's just say when we put a number next to a letter, we put a number next to a variable, it always just multiplies, period. Okay, so hopefully that makes sense. We're going to do that with this assignment here. Last time I was very vague with this. I'm going to try to be more specific because I'm supposed to help you after all, right? So let's be specific. This assignment, question number 5, is not in here. So we submit our answer. It likes my work. Great. We finish question 4. When I go on, it actually jumps to another section. Okay. This is called well, I can say this. This is called an algebraic expression. We just wrote that. There it is. That's question 4. And an algebraic expression has numbers and variables in the same expression. So it's a form of symbolic expression that we talked about before, a symbolic representation of something, because we're using letters to represent numbers, possible numbers, hypothetical numbers. It's all up in the air and abstract, and that's part of what algebra is all about. If you can write an algebraic expression to generalize the entries in a process column, you can find a function rule to show the relationship in the table. Technically, it is a function rule. See, this is an expression because it has numbers and variables. This over here, you can call it a function rule. You can also just call it an equation because it has an equal sign. Once you have an equal sign, you no longer call it an expression. It's now an equation. An expression is like an unfinished sentence in math. It's like, I went to the store and, or something like that, like a run-on sentence that doesn't really go anywhere. It's just a statement. That's what expression means in math. Whereas if I have an equation, I have both parts of a sentence. So it's like a full statement here. This is equal to that, not just that. Okay? So that's why equal signs are important, and understanding the difference between an expression and an equation is important later. Okay, so now this stuff is question 6. See, so we have to go finish question 5 first. Okay, Benton Middle School 7th grade science classes are building and maintaining a vegetable garden. The border of the garden will be rectangular with an interior, the border of the garden will be rectangular with a fixed interior length of 6 feet. The students will build the borders of the garden with cinder blocks that measure 1 foot by 1/2 foot. In addition to creating a border, each cinder block has 2 holes in it that can be used to plant small herb plants. Let's make sure we understand what a cinder block looks like, just in case you're not sure. Cinder block. Let's just look at a quick picture of a cinder block. Looks like that. So they're building a garden by building a wall out of these, and see the 2 holes like they're talking about. And it's 1 foot long and 1/2 foot wide, each cinder block. That is what they're saying in this assignment. So these are cinder blocks. These models show the 2 smallest ones. Notice they said a fixed length of 6 feet, fixed interior length of 6 feet. What that means is this length right here from this side, from the left to the right, is always 6 feet. So what I need to do is think about the other ones, but they are allowing this length to change, the height of our square here. Still 6 feet wide, but this one's taller. It's 2 feet tall. And notice, because they overlap, there are 2 cinder blocks here on the left side and 2 on the right side. And half of the cinder block is part of the wall before, and half of the cinder block is actually the height inside in this white area where they'll actually do gardening. Okay? So let's draw a couple more. We're going to, the way I would do this, something like so. And we'll make one more. Now, we're going to have to, since we're on a computer and we're drawing this by eye, it's not going to be perfect, and that is okay with me. But what we can do is we can just draw lines. So we need, notice the top and the bottom are always the same. They're always 1, 2, 3, 4, 5, 6 cinder blocks wide. So let's just try that first. 1, 2, 3. Oh, actually put 3 on each side, right? Is this beautiful? No. Is it doable? Sure. Could I do better? Probably. Would it be worth it to me? Probably not. All right, so I got these lines in. Let's put the other lines on the bottom too. There, I believe that's 1, 2, 3, 4, 5, 6 on the bottom, 1, 2, just like up here. Not as pretty, but that's fine. So now these ones had 2, these ones had 3 on each side. This one's going to have 4 on each side. So 1, 2, 3, 4. How lovely is that? All right, and this one's going to have 5 on each side. 1, now, if I were drawing this perfectly, then each of these would be the same length, but they are not, and that's my bad. There are a lot of things to think about there, but that's okay. So I'm gonna do my best. But sometimes you have to be careful about that because I need 1, 2, 3, 4, 5, 6, and I made the last one really, really far away. And you can at least try. Still not that good, but that's okay. All right, and this guy, very boring. One. Wow. Are you enjoying watching this? All right, there we go. We got it. And now you can count them. So notice the first one has 1, 2, 3, 4, 5, 6, 7, 8, and then 8 along the other half. So this, when I have a 1 by 6, I'm going to make my table, because it says to make a numerical representation. Numerical representation, if you remember from up here, numerical representation is a table because it keeps track of the numbers and it puts them in their places. So our two variables that we have in our table are close enough. Our two variables are, we'll say height. I know it's not the actual height, but that's what it looks like in the video, in the picture, right? The height of a rectangle here, how tall it is. That's what's changing each time. 1 foot, 2 foot, 3 feet, 4 feet. And number of blocks, all right? Okay, so when the height was 1, this up here, we have a total of 16 blocks. When the height was 2, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 9 on the other half. So for a total of 18. You can count them yourself if you like. I guarantee you there are 18. 3, well, I'm going to go fast. I'll tell you this is going to have 4 and 6 for a total of 10, and double that and I get 20. And you're starting to see the formula here, I hope. And go, oh, I see what's going on here. 4 is going to be 22. I don't even have to count because I know what's going on. What do you notice? When I add 1 foot to the height of the rectangle, it requires 2 more cinder blocks. There. We noticed that, right? It adds 1 on each side here. There used to be 2 on each side, now there are 3 on each side, and there are 4 on each side, then there are 5 on each side. That's what's changing with the number of cinder blocks. The top and bottom are always 6 because they said this never changes. The width of the rectangle never changes. Write a symbolic representation. Well, here's what we notice. We notice that we have 6 on the top and 6 on the bottom. That's 12. But before that, we would have our length of our side. If it's 1 foot, I get 2 blocks. If it's 2 feet, I have 3 blocks. If it's 3 feet, I have 4 blocks or whatever. So we have to think of a way we're counting it. This might be tricky. So here, I'm going to show it a way that I would do this. I would say we have 1 foot, I have 2 blocks, right? That's X, whatever the height is, we'll make it H. H plus 1. That is how many blocks it takes to make each side, right? H plus 1, so that's 2 blocks here, 3 blocks here. If this is a 2, this is a 3. This is a 3, it's a 4, and so on and so forth. Plus 6. That's actually H plus 1 plus 6. Great. That is actually half of it. So whatever this is, I add 1 to it and I get this side. And then I add 6 more. But that's half of the square. So instead of overthinking this, I know that that's half the square, right? I'm going to say 2 times that. Or 2 times H plus 7. And this is why we have to get used to dealing with weird ways, like multiplication and distribution and all of those things, because there are lots of ways we could write this. If I multiply the 2, I can distribute it 2 times H and 2 times 7, something that we've learned a while back, I hope. And we get 2H plus 14. So the number of tiles we need, T, is equal to 2 times the height plus 14. Now here's the really cool thing about algebra. That means that I just have to take this number here, multiply it by 2 and add 14. Let's see if it works. 1 plus times 2 is 2, plus 14 is 16 feet. If I have 2 times 2, that's 4, plus 14 is 18. It really does work. Now, it takes the way we're used to counting it, it turns it into a different looking thing, but that is okay because it's doing the same thing. And that's why we need to learn like, oh, the order of operations, 1 plus 6 in the parentheses. And then I distribute the 2, and I get this. So this right here is what I'm looking for. Is this the only way? Oops. No, it's not the only answer, but it's the one I would write. Okay, each cinder block can hold 2 herb plants. Okay, so this is how many cinder blocks I need. Why did I use T? Oh well. Let's change that to, I think I was saying tiles. Let's say that's cinder blocks instead. Control Z. What has happened there? Okay. Cinder blocks. That's what we'll do. C for cinder blocks. Okay, down here. Now we know that the number of cinder blocks is 2 times the height plus 14, right? Each cinder block holds 2 flowers. So for every 1 cinder block, I can hold 2 flowers. So whatever this number is, what do I do to it to get the number of flowers? Think about that. And think about what you would write down. And now I'm going to write it. So the number of flowers is 2 times the number of cinder blocks. Flowers equals 2 times 2h plus 14, which if you distribute F equals 4h, 4 times 2 times 2 makes 4, plus 28. That's the answer I would write for that one. Okay, making a graph. We're back to our assignment. Lots of talking to do. Oops. So next, we're going to use our information to make a graphical representation. We are back to our good friend and his tiled pool, not the flowers. We're back to the tiled pool. So the pool was 1 by 1, 2 by 2, 3 by 3, and it had 8, 12, 16 tiles to go all the way around it. Okay, so Anthony is making a graphical representation to see how he represents all the data in his pool situation. Just so you understand, this is the graph we want. So when you go into here, you're going to say, well, I would make the, go to paintbrush, I'd make this a 4 or a 6, so you can see it easy. 1 by 1 required 8 tiles. 2 by 2 required 12 tiles. 3 by 3 required 16 tiles. Oops, that was not very pretty. And there we go. We got a graph. Okay, so that's what it's asking for first. Okay, and that's great. That's the answer to question 6. Next, they say, what if I graph this? Y equals 4x plus 4. Now remember, the formula we had was the number of the pool length, sorry, the number B, the number of tiles, or T, the number of tiles, equals 4S plus 4. So this is B equals 4S plus 4. That's what we had before, and now we have a Y and an X. Now when we say Y and an X, we usually are saying we are just gonna let any numbers be plugged in for the domain and the range. X can be any number, Y can be any number. So instead of 1, 2, 3, 4, 5 as the points I'm graphing, I can graph anything in between, which is why when you graph a line, it's a solid line because everything on that line works. You're allowed to plug in any of those numbers and it works. So what are the domain and the ranges of this function? Well, they are all real numbers. That's what we say. We say all real numbers. If you don't have either a situation in real life or a situation mathematically where some numbers don't work for some reason, then every function you ever get has a domain and a range, well, at least a domain of all real numbers, okay? So remember that. All lines that we're gonna graph will have that domain and range. So when I get here, I'm gonna say, what are the domain and range of this function? This function right here, this is a y and an x. Then its domain and range are, domain and range are both all real numbers. I want you to get used to that. This is something you will say in Algebra 2 as well, a little bit in geometry. What we're saying is x and y could literally be any number. Not at any time, because based on what x is, that affects y. But I can plug in anything for x, and by plugging in the right thing, I can choose and make y whatever I want as well. Okay, so that's what we're saying. Now, in Anthony's tiling pop situation, he doesn't deal with fractions of squares. We're not having 2.5 foot long pools or 4.25 foot long pools. We're only having counting number pool lengths. So that means his domain is, you could say, positive integers. Positive integers. You could also say 1, 2, 3, 4, ... n. Remember, when we're talking about counting numbers, we like to use n. Range is also positive integers, but here's the weird thing. We would say, well, we have our numbers here. The domain, oh gosh, we have them way up there. Let's go back to this assignment because it shows it right there in front of us. The domain is 1, 2, 3. The range is these numbers. So we could say something like this. Rather than just saying positive integers like the other one, I might say something like 8, 12, 16, ... Remember that ellipsis means going on forever until you get to, well, we had 4n plus 4. So anything where I plug in an n, these guys, and I use the formula, will give me the range. So if n was 100, I would get 404. 4 times 100 plus 4, and so on and so forth. Okay, oops, I used the wrong type of thing. Remember, we always use braces when we're listing numbers. We use those weird ones. All right, question number 8. Getting there. This is taking forever though, sorry. All right. Here, we have numerical representation. I'm just gonna tell you they're right here. So you can copy them out of the assignment if you want, but I'm not gonna write them down because it takes too long. But notice, this is the same situation, except people are putting a second set of corner tiles around the outside. So instead of having the lengths times 4, and then adding the 4 corners, we're adding the 4 corners twice. So instead of adding 4 around the corners, we add 8 around the corners. So the numerical representation, instead of 8, 12, and 16, we have 12, 16, and 20 because there are 4 extra tiles being used in this formation. So this is the same thing with a pool. Tiles go around the outside, but it has 4 extra corner tiles here. So the numbers here are just 4 bigger than we've been dealing with in the past. We could say it's still, when this goes up by 1, when the length of the sides goes up by 1, this still only goes up by 4 because the only thing changing is these sides, not the corners. So the verbal representation is kind of the same as the previous one. It only goes up by 4s. The graph looks similar, but instead of earlier where it started down lower, the whole line is up a little bit because it starts out with 8 instead of 4. So the previous line was down here. We're going to talk about how to do this graphical representation in our next class on Desmos. All right, and they do a lot of math stuff. Wow, they did it a lot of different ways. Now, these are different ways you could do it. You could have this way, the top
4
one.
lines, line 1. T equals 4.
Oof, that's ugly. Okay, the second one is the same thing as the first one, only we have not distributed this 4. The third one is a very, very fancy way to do it that I doubt anyone would come up with, but this is another way you could also come up with a formula and count the squares, and it will also work. And then this one is without as much distribution. So these are all formulas that would work for this. Okay, the first one is the one that I would probably shoot for first, but the other ones are also legitimate. Okay, so these are the answers. Please write them in though, make a graph. I would count on my graph by 4s, not 5s. That would be much easier, but make the graph, okay? So I would make it go up by like 4, 8, 16, 12, and so on and so forth. That'll look much better for your graph than the one that they gave you, which counts by 5s. Counts by 5. See, all none of the dots line up. It's much easier to have it count by 4s. That'll work better, I promise. Okay, almost done. Question number 9 is part 5. That's back to our flower bed thing. Okay, I'm not showing you question 8 because you can literally copy it out of the assignment. I just showed it to you. So back to 5, we're dealing with the cinder blocks and the flowers and all that stuff. What it's saying is they've decided we're going to make a relationship to the garden width and the number of cinder blocks. Okay, so I'll show you how I would do this. So I noticed that the number of cinder blocks goes up to 22. The height goes up to 4 so far. I'll have it count up to 5, and I'll have this guy count up to about 30. So x's will go up to 5, y's will go up to 30. That way I'll hold all of the numbers nicely. And I like that it counts by positive numbers. All right, so we're going to have 0, 1, 2, 3. Oops. Now notice, I am very carefully making sure that the numbers are the same distance apart. So right now I'm counting 1, 2, 3 lines over for each number. 1, 2, 3 lines, 1, 2, 3 lines. You can't just arbitrarily choose one distance for one set of numbers and another distance for another. So once you start, you have to keep following that pattern. Okay, if you do something else, if you just kind of like randomly, arbitrarily be like, I'm going to make this one further away because I like the way it looks, then tough. Numbers, 5 is the same distance from 6 as it is from 4, and it always has to be. You can't just change that in math. So don't try. Okay, and then I'm going to have this guy count up by, oh, I don't know, let's go up by 4s or 6s. I need to go up by to 30, so I'll go up by 6s. 2, 4, 6. I think there are 30 tiles, so let's try 1, 2, 3. This is 6. 1, 2, 3. That's 12. 1, 2, 3. That's 18. 1, 2, 3. That's 24. 1, 2, 3. So I'm really making every square be 6, if you notice that. And that's good because if you remember, our table up here starts 1, 16, 2, 18, 3, 20, 4, 22. Those are about in the right range. 1, 16 was our first point, so let's do that point. this is what I want you to do. 1, 12, 14, 16. So since I counted up by 2s on these squares, 2, 4, 6, 8, 10, and since the numbers we have are all 2s, we are going to get nice points. They're all even numbers that line up nicely on our graph. So on the table that was up above, I can scroll up one more time if you want, but you get the idea. 1 went with 16. It took 16 cinder blocks to make a 1 by 6 garden. It took 18 cinder blocks to make a 2 by 6, and so on and so forth. All right. So when we get our line, it's going to look like this guy. If I kept going, 5 by 6 would make us 24, and 6 by 6 would require 26 cinder blocks, and so on and so forth. So there's our graph. If I were to graph this function, its domain and range would be all real numbers, because it has nothing to do with anything. It's just y and x, and so I can plug in anything. Cinder block problem is discrete, however. Its range is, well, domain is going to be 1, 2, 3, 4, and so on and so forth. And range started at 16 and kept going up. 16, 18, 20, 22. 16, 18, 20, 22, all the way up to, well, whenever we have an n, we multiply it by 4, we add, no, multiply it by 2 and add 14. That's what we had. 2n plus 14. After students, blah, 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 she said it would be too difficult to reach the center of a 6-foot garden. She decides to alter the design to make it 4 feet instead, create each of the following representations, the width of the garden, blah, blah, blah. You know what? I'm out of time with this one. I'm going to make this one be you. You got to try your best. We'll go over it. All right, I'm done. Have a wonderful day. Stop, share.